Hello dear friends, a great welcome to this series on Idea Statica member. Myself Jarajan P. This is tutorial number 32, and with this tutorial we'll start a new session on Idea Statica member module. If you remember, in the last 31 tutorials we had an elaborate discussion on the design and verification of structural steel members using the connection module of Idea Statica. So naturally, the first question would be, why Idea Statica member? The answer is simple. While Idea Statica member software performs the design and strength checks of a steel structural members like any other tools available in the market, such as SAP 2000, ETABS, etc., it's also capable of performing additional verifications, namely the stability and buckling checks. Therefore, in addition to conventional members, it could be effectively used in the detailed investigation of heavily loaded members such as plate girders, bridge deck supporting beams, and equipment supporting beams used in industry. So let us start the first tutorial on Idea Statica member, which is essentially an introduction session. And this session will be later followed by a demonstration to highlight its application. So let me take you to Idea Statica member module. So when we open Idea Statica, the screen looks something like this. So we have the various heads like the connection, the member, etc. So here we would like to make use of the member module. So you can just double click it. So it may take a little bit of time. So in the member module, we will be able to either upload an existing project, or you can straight away start from the new project. So let me just keep it down. So for example, suppose that we are interested in starting a new project. You can just double click the new. So this will help you to identify the various project details, input the various project details. For example, you can type here the project name. Project name is the name of the folder, right? Where you will be storing all the project files related to this project. And this is a project folder. And you can also select whether it's a steel beam or a concrete beam. And the design code, obviously the Idea Statica, as you know, it supports many national as well as international codes. And for example, in this case, I have selected the Euro code, and you can input the steel grade to be used. You can have either S235 or S275 or S355, and the concrete grade. And here it provides you the various geometry types that you can consider for the project. For example, if you select, this is the label to be selected for the beams, and this is the label to be selected for the columns. And if you have a bent up member, you can select this one. And in the next one, that's the spans. You can input the spans. Okay, you can input this straight away the total length, and you can divide it later as well. You can here provide the cross section, which is nothing but the cross section of the analyzed member. So here I can, for example, if I input all this data, I will have a standard template that is coming over here. For example, in this case, I just want to go back to my original file. So I will just select a simple file for the explanation of the introduction of this module. So here, let me just open this existing file. So as you can see that the project name was lateral restraint. So I'll just open it, and so that I will be able to explain what are the input parameters required for making a proper functioning, proper working of this Idea Statica member module. So this is how the Idea Statica member screen looks like. It is you can say that it is almost similar to the one that you have seen in the Idea Statica connection. So on the right side, you will find that there are many labels which requires the input parameters to be fed into the program. For example, here we have the analyzed member. Now I just want to tell you one very important thing. In Idea Statica member, what exactly we want to do is we want to cut out a part of the structure. Okay, we want to analyze not the whole part. We want to analyze only a small part of the entire big structure, and we want to subject this a small part to a detailed investigation. Or in Idea Statica member, we rather subject a cutout structure, right? a structure which is separated from a small segment of the structure separated from the main structure for further detailed investigation. So we have analyzed member. Now, as the term suggests, analyzed member is the one which is to be analyzed and it is to be subjected to a detailed investigation from the point of view of the strength, from the point of view of the stability, buckling, etc. So, for example, here is given a default name AM1, and as you can see that just like the connection, AM1 requires some parameters to be provided. For example, it asks you provide the cross section. Okay, anyway, in the next tutorial I will come with a new what I want to say, the sample tutorial. So a detailed coverage of all these topics will be, all these labels will be covered in that next tutorial. This is just for the introduction, and here you will find that the cross section, and here you will find that the offset EY and EZ of what we call as the analyzed member. So in this case, I have kept an EZ of 119 in order to keep the top of structures TOS of the analyzed member and the related members at the same level. Okay, and here again you will find that it provides you what is the x coordinate of the beginning node and the end node, and therefore in this case a length of 6.5 meters is given. So remember, analyzed member is the one that is shown here. This is the member, right? And which is to be analyzed and then subject to a detailed investigation from the purview of the strength and the stability. Now, next level is you can read it as a related members. Normally, we designate it as RM, related members. Now, what are related members? Now, as you can see that, for example, here I have two related members. One is RM5. So this is one related member, and then there is another related member, RM6. So this is a related member. Now, what are these RM5 and RM6? So they are known as the related members. So related members are the members to which the analyzed member is connected, right? So you can see that this is a joint where AM1 is connected to the RM5, and this is a joint where AM1 is connected to RM6, right? And here one very important thing I would like to highlight. Idea Statica uses the shell elements for the entire analyzed member AM1, whereas as far as the RM, that's the related members are concerned, a small stub type portion, it is being modeled fully using the shell elements. So you can see that here there is a stub element. Okay, this is a part of this related member only, wherein the full detailing using the shell elements is done. And for the balance portion, as you can see that the balance portion of the related members, it is not, it is denoted or it is indicated through the straight lines, indicating that these parts are being modeled using the 1D beam elements with the 6 degrees of freedom. Okay, so and as you can see that, for example, if you look into what are the parameters required for for the modeling of these related members, as usual, it asks you the cross section, it asks you if you have any offsets and the rotation angles. It will also tell you what must be the length of the members to be modeled. Okay, and one very important thing here is that regarding the supports, or I would better call in terms of the structural analysis as the boundary conditions. Now, as you can see, regarding the analyzed member, okay, so let me just push it once again, AM1, you don't have any provisions here to specify the supports, right? It will not ask you whether you want to have a rigid analysis or whether your supports are to be rigid or to be pinned or something in between. Now, why it is not provided intentionally? Because here, as you can see that the AM1, it is connected to the related members through the connections. Now, depending upon the connections, it automatically assumes the required degree of what we call as the rigidity. Hence, you can see that the support conditions are being properly investigated by Idea Statica itself, and it do not require any kind of other input from the user. Now, as far as on the other hand, for the related members, it asks you to provide what must be the boundary conditions to be used at the ends. For example, in this case, I used pin supports. According to it, you can see that beginning, the X, Y, and Z movements are being, translations are being prevented, and at the end also, okay, the X, Y, Z translations are being prevented. That's there in, you can say that they are truly the pin supports. So for example, this is for the RM5. You can see that here, this is one support. You can see that the three directions it is being restrained, or the translations are being restrained in the three directions. Okay, so means in the Idea Statica member, you can directly specify the support conditions for the later members. right? So now other very important head is the loads. Now, Idea Statica provides you, Idea Statica member provides you the various ways in which the loads can be applied. And frankly speaking, this facility is not available in any of the what we call as a 3D software like the SAP or to SAP 2000 or ETABS. And because applying the loads in the right location is very, very critical. Obviously, when the member to be analyzed is very deep and the loads are very large, right? So here, as you can see, for example, let me just explain you what are the input parameters required for the simulation of the loads. Obviously, as usual, as we have seen in the Idea Statica connection, the load cases are being indicated by LEO and LE2. So in this case, what I did is, so if you see the properties, so Idea Statica provides you whether you want to define a design load that is corresponding to the ULS, that is nothing but the ultimate strength limit state, or you want to define a particular load under what we call as the service load conditions as well as characteristic. So in this case, I have provided a load of LE1 that will enable Idea Statica to design this member. So here you will find that the loads, how these are being indicated. So for example, it will ask you what must be the beginning location of the load, the end location of the load, and what must be the kilonewton per meter, and whether the location is very important. Look here. The location, Idea Statica allows you to apply the load either on the top or on the bottom or on the member axis, left to right edge. And this facility is not available anywhere because the load application is very critical when we are going for the further detailed investigations relevant to the stability, because we know that the lateral torsional buckling is a phenomenon that essentially is governed by how the load is being positioned with respect to the compression flange, etc. And so Idea Statica provides you a nice simulation of the applied load, and it also provides you what must be the width of the applied load. This is also very important. So here I have just provided as 100 mm and applied on the bottom flange loads. Okay, so this will be taken up later in detail, and it also regarding the end members. So these are the loads that is being applied on the AM1, that's the analyzed members, and on the latent members you can also apply the loads. And here I want to tell you one thing, there are two schemes you can, so please remember this part of the structure, right? This part of the structure which consists of three members, AM1, RM5 and RM6, it is being just cut out. It is just separated from a big structure. Accordingly, obviously, from the main structure analysis, it is possible for us to obtain what are the reactions at these two, at the ends of what we call as the related members. And these support reactions can be applied at the ends of these related members, so that your this is a small structure which is just cut out from the main structure. It matches with the force conditions, or it simulates the force conditions exactly similar to the full structure. So means that what I want to tell you in terms of our old engineering mechanics, I will rather say that this three-member assembly should be in equilibrium, right? So means I just split this segment of this structure from the main body, and I need to ensure that all the forces are being marked properly here. That means this is nothing but this segment should represent the free body which is in equilibrium. Okay, so accordingly, this Idea Statica will permit you to input the loads at the ends of the various related members, and please remember that the forces to be applied at the ends of these related members, these are to be taken from the full structural model, which may be either in SAP or in ETAPS or in any other software. Okay, so and obviously you can also model the loads that are required for the serviceability checks, right? Now, coming to the next one, that is the connections. Now, connections, please remember here. So, connection means here we are going to model the connection between the analyzed member and the latent member. So, let me just zoom it. So, you can find that yes, I have modeled a connection over here. Let me just zoom it a little bit so that you'll be yes. So, you can say that I have modeled an end-to-plate connection between the analyzed member as well as the latent member. And how this will be done, it is very simple. What we need to do is that connections, whenever when we want to model a connection between an analyzed member and the latent member, we have to press connection. Okay, So when I press connection, obviously suppose that here I have already modeled the connection. I want to make some changes. So what you can do is that you can edit connection, right? You can just press this button. So when you press this button, what Idea Statica will do is it will obviously take you to what we call as the connection module of Idea Statica, right? And then it will allow you to make the model. And please remember here one very important thing: Idea Statica member do not go for the connection checking, right? It will not check you any connections. If you want to verify any connection, obviously you have to do it using Idea Statica connection only. So in this case, let me just press it. So edit connection. So obviously it will take you to what we call as the Idea Statica connection user interface UI. So yes, as you can see that it is connection is started, and you will be shown the connection between these two members, right? And if you want to make any kind of a modification, you want to generate a connection, all the connections can be generated in the Idea Statica. So as you can see that the connection that I have already developed, it is already given here AM1 and this are RM5, etc. Right? So this is how you have to generate. Anyway, all these features will be dealt with in example tutorial that will be taken up next. Okay, and then the other very important aspect is, let me just smaller more. Okay, another very important thing is the operation. Now here in the operations, so let me just, okay, so I think that here I may have to go for so okay, fine. So let me just tell you what this operation is meant is. This operation will tell you, it will allow you to add. Okay, here I have to select the analyzed member. Okay, just a minute. So what do you mean by the operation here is, whenever we go for the detailed investigation, in many cases, suppose that I'm dealing with a plate girder, I may have to add some kind of a stiffness, to improve what we call as the web capacity, or to improve what we call as the shear buckling. I may have to add some kind of a stiffness, or if I'm in some cases I may have to add some openings which are coming through the girder. So these operations will help you to add a number of what we call as the manufacturing operations on the analyzed member. So if you press operation, you'll find, look here. Here you can add a new opening, and you can add a local transverse stiffness, longitudinal stiffness. Okay, so many kind of operations can be added in the analyzed member for the detailed investigation. So once all that is done, you can say that this entire input parameters are over. Now it is a time that you can go for the calculate. So let me see that now when I go for the calculation, it may take some time. I just want to tell you that Idea Statica member in fact has got three types of analysis. That is very important. One is known as MNA, which I am running right now, material nonlinear analysis. So this for any Idea Statica member, this is the first analysis to be performed, right? And secondly, I have got LBA, that is what we call as the linear buckling analysis. And then what we have is what we call as the MNIA, that is we can call it as the materially and geometrically nonlinear analysis with imperfections. Now what these are meant to us, now as you can see that one analysis is over, that is what we call as the material nonlinear analysis. Now let me just take you to the check section. So this is something like what we have in Idea Statica connection also. And here you will find that we are right now in MNA, that is the material nonlinear analysis. So what does this result provide you? So this result will provide you, for example, the capacity of the section, right? The capacity of the section. So remember, MNA do not consider any kind of buckling. It simply provides you what will be the capacity of the member just based on the material strength, just purely based on the material strength. For example, in this case, as you can see that the results are being displaced on the right side, you can see that the stresses are going up to 128 and the various parts are being given here. For example, these are analyzed member, latent members, etc. Now, it also provides you whether you want to see a model with the mesh or without mesh. For example, here, if I press mesh once again, you will find that no meshing is being required. So let me just provide the meshing. And For example, you can see a deformed shape or an undeformed shape. So for example, if I just press it once again, you will find that this is an undeformed shape of the model. Now, suppose you're interested in finding what is the bending moment. You can go for the internal forces over here. So you can just press the internal forces and the model. So as you can see, look here. So this model provides you what are the bending moments. So you can see that this is a bending moment, this is parabolic, and it also provides you the various the bending moment diagrams for the related members also as shown here. And so now coming to, for example, this is your the bending moment about the major axis. Suppose you are interested in the shear force diagram, you can just press the VZ and that provides you. So look here, so this is how the VZ is a linearly varying, right? So it provides you the shear force diagram for both the AM as well as the RMs. Now coming to the stresses, you can also obtain so suppose we don't require this internal forces no more, and just press it once again as usual. So you'll find that we have a good diagram now. So you can just press, for example, the stress if you are interested in obtaining the stress distribution. So that takes a little bit of time for the display. So you'll find that here the material, the loads are at a very lower level. So as you can see that the stresses are somewhere around, only hardly around say 75 Newton per square. And whereas the material strength is 275, because this is just a sample example which I have taken for the introduction section. And you can also see, for example, the strain profile distribution. So obviously, as is shown here, the strains are at a very low level. You can see that is at 0 level because the stresses are too low, right? And this will also enables you to check whether the deflections are within the proper limits or not. For example, suppose you are interested in what we call as the vertical deflection. It provides you the vertical deflection, and obviously these deflections are to be checked. For example, in this case, it is subject to the maximum 10.5 mm, and these have to be checked under the obviously in our case LE2, and LE1 is the case which is selected for what we call as the ULS ultimate strength check, and here you will find that for the ULS, right, that's the ultimate strength limit state. You let us see what are the stress levels. So yes, you will find that yes, the beam is fully utilized up to 275 mm. And still, please remember that in the Euro course and in majority of the international course nowadays follow the so-called the plastic limit of method, wherein we calculate what we call as a plastic moment of resistance on the assumption that all the fibers are fully yielded. So looking into this sketch, you will find that only the some fibers are being yielded. So means that the section do have some more capacity, or we can say that conclude that from the strength analysis, we can say that the section is good enough. Now, this part is good enough. You can carry out both for a restrained beam or an unrestrained beam. And now coming to the LBA, now this LBA is what we call as the linear buckling analysis. Obviously, these two buttons, LBA, that is the geometrically and materially nonlinear analysis with imperfections. It will be used only when the user is interested in the detailed investigation of the buckling phenomena. For example, once M&A is complete, it is important that you just switch over to the LBA, right? That is another analysis. That's a linear buckling analysis. And obviously, the purpose of the linear buckling analysis is just to see how far the section is stable with respect to the buckling. And the result of this linear buckling analysis will be provided in terms of the amplifier. That means how much the amplifier, what must be the amplifier, or what must be the multiplier for the working for the design loads to reach the so-called Euler's buckling loads. Okay, now let me just simply calculate the linear buckling analysis. Let me know. So obviously this will take some time, and as I told you, this must be done only in cases where the buckling is to be investigated. Obviously, suppose that a beam is laterally unrestrained, you have to carry out an LBA, right? So LBA is basically is a elastic analysis, the buckling analysis, and it provides you the possible buckling shapes and what are the multipliers to the design loads to reach the so-called Euler buckling loads, and also tells you whether the beam is very critical as far as the buckling is concerned or not. So here, look here. So you can see that this is how it has provided the results of the linear buckling analysis. You will find that 1.22. So as far as, so we have to consider only what we call as the ultimate limit state loads LE1. It provided me how many, 6 more shapes. For example, suppose I am interested in the mode shape 1, you will find that 1.22 is the factor. Means that I have the factor of safety of 1.22 against the buckling. So if I just press this, so you will find that the buckling more shapes. So this is my user. Okay, so you'll be able to obtain the so-called buckling shapes. The way this will provides you what we call as the various buckling more shapes. So here, so if you just zoom it, because here let me just. So here you will find that yes, there is what we call as the buckling of the flange. Yes, they are being subjected to a lateral bending, as you can see from here. Whereas the tension flange is at one location, the compression flange is subjected to the bending. You can improve the multiply the scales also for the better visibility. So this is all about the LBA. Now there is another very important analysis, that is what we call as the GMNIA. That is a geometrically and material nonlinear analysis with imperfections. Now what is this? What this is meant to you? Once you find that the LBA is very critical to you, the Idea Statica member, it also provides you one more opportunity for a detailed investigation, wherein it provides you some kind of an imperfection to be, okay, input into the model. For example, suppose that, so you know what these imperfections are. Imperfections comes from a variety of sources, and if you go into the Eurocode, it provides you a very good detailed account of how the imperfections are to be calculated. Okay, for example, it provides you depending upon the buckling curves, the imperfection has to be L by 200, L by 250, etc., etc. And when there is an LTB, there's a multiplier of 0.5, etc. You have to calculate the imperfections in terms of mm, and then you can input here this imperfection and again carry out a geometrically material nonlinear analysis with an applied imperfection. So these are all about the various analysis types being covered in Idea Statica member. And just like as we have seen in Idea Statica connection, we can go into the report. But what I found is Idea Statica has to improve a lot in including what we call as the important numbers in the report. Presently, I don't like the way in which they have put up the report. It do not provide any kind of an additional information. So that's all about for this introduction tutorial. Obviously, in the coming days, we will I will take you to the various tutorials covering the detailed investigation of restraint beams, unrestrained beams, plate girders, bridge ducts, and the beams with openings, etc. So that's all. Till then, bye bye and have a nice day.